All right, so what we're dealing with here is we're going to find volumes of solid objects, all right? And I just showed you that video that illustrated what we're talking about here. But what we're dealing with is we have a region in the plane and we're revolving it around a line. And that, because we're revolving it, it's called a solid of revolution. Okay, because we're spinning it around the line. The line is called the axis of revolution, and the simplest one of these is a cylinder or a disc. Okay, and basically what we've done is we've taken some kind of a rectangle, which you can see here. We have this rectangle with a width of W and a height of R, okay, and we now have spun it around this axis, okay, to form yeah, like a wheel, okay. So here, I'll outline it for you since it's a little hard to see in yellow, okay.
Never thought of a wheel that, like a wheel as an object that is based on something rectangular.
Yeah.
A wheel is something that is the furthest from rectangular object, but then it is based on it. And
yeah.
It breaks my mind.
It really is. But let's think about the volume formula that we learned a long time ago for this, which is a cylinder, this disc or cylinder. We know the volume is pi r squared times the height. Well, using the letters that are on the diagram here, the radius r is the capital R, and the height of this cylinder is that W. Okay, we use W because it's going to be the width of the disc. All right. Now, let's say that you know, as long as this R is constant, that's easy, all right? That's just a normal old cylinder. But let's say that it changed, okay? For example, here we have this function, all right? We have this function, and this function is R of x. Notice the radius is going to change dependent on what x is, okay? So you'll notice what we have here, again, we're kind of going back to that whole idea of the Riemann sums to figure this out. One disk is going to be W times R squared times pi. However, if we want to generalize this, the width is going to be this delta x, and the radius is going to be, if this is the point where we have x sub I, whatever that x coordinate is, then this is going to be r of x sub I. Okay? So just this rectangle is going to have an area of delta x times r of x sub I. Okay? If I were to form a disk with just that rectangle, like you see here, okay, here's r of x sub I, all right? And the width of this, you can see down here, is the delta x. All right, if I were to do that, okay, that cylinder then, if I did pi r squared h, pi times the capital R squared times the height of that disk is the delta x. All right, well, what am I going to do with that? Well, to find the volume of this entire object, I'm going to cut it into a bunch of disks. Okay? And you guys can kind of see where we're going with this. It's just like what we did with Riemann sums. I'm, instead of cutting it into a bunch of rectangles, now I'm cutting it into a bunch of discs. And if I do n discs, that's going to approximate the volume. So how do I get a better approximation?
Increase the number of discs.
I increase the number of discs, and that's why we are going to use, as n approaches infinity, or as that delta, that norm, okay, is what it's called. The width of the disk is approaching 0, all right? The limit of the sum we're familiar with is our integral, and that's where we get the formula for our solid of revolution right down here, okay? The volume is pi times the integral from a to b of the function squared.
Can you show me how the other formula led to this one?
Okay, well, it's just like what we did with the Riemann sums. We're taking the limit as that norm, or that difference, the width of the disks approaches 0. That's going to happen as n gets towards infinity. And that was the same thing we saw back when we did the Riemann sums. The limit of the sum is the integral. And delta x is dx.
Are we also going to do the area around, or just volume?
Well, it's just volume. I mean, there are ways to do surface area.
I was thinking
Okay,
of
but-
pi r thing. No.
Yeah. We're gonna do volume for this one, but there is a way you can do surface area. But. All right, so that's the basic formula that we're going to use here, and if you just keep in mind the fact that we're dealing with a cylinder, basically, pi r squared times the height. Well, what's the height? The height is the dx, and then we've just got to add all of them up from a to b. So we're doing the integral from a to b. Okay? Now, the disk method, we can do both with vertical disks or with horizontal disks, okay? If we're given a function that's defined in terms of y, we can do the same thing. Notice, though, the difference here is that we're going to go using y coordinates as our bounds. It's the integral from c to d in this case.
Are you going
Okay.
to get the same volume, because it's going to be a different shape?
Well,
Dependent
in this one it looks kind of like a quarter circle. So if this one, you've revolved it this way as opposed to this way, it'll give you a hemisphere either way. But you won't necessarily get the same volumes. Okay? That's why which way we're revolving it is important. Okay? For example, we want to find the volume of the solid formed by revolving the region bound by the graph f of x equals the square root of sine x. Okay? The x-axis and x between 0 and pi. So we're just going from 0 to pi, all right? Now we're revolving it about the x-axis. If I tried to revolve this around the y-axis, that would look really kind of goofy. I'd have this thing kind of looks like this, and it would be flat on the bottom.
Would look like a hole.
It kind of would look like,
A donut, right?
yeah, a donut with no hole in the middle, because it would all meet like in the middle,
Oh, there's no hole.
and that you cut the top off of, you know? I don't know if you can tell that's three-dimensional or not. Maybe.
What are
It's like or maybe a bagel that blew up so big that the hole is gone now.
I see.
And now you sliced it in half, you know? All you need is some cream cheese and you're good to go.
Optical illusion.
All right.
Yeah. like seeing it twice.
But that's revolved, that's if we were to revolve this about the y-axis, okay? That's going to have a different volume than this little egg-looking thing that we get when we revolve it around the x-axis, okay? So pay attention to which way. That actually turned out pretty good. Pay attention to which way it's revolving, okay? But let's actually look at how we would use our formula with the disk method in this case, all right? This is in terms of x, so I'm going to be integrating with respect to x, dx, and I'm going to use x coordinates as my bounds. So what are my bounds going to be here?
0 to pi.
0 to pi, okay? 0 to pi. The formula says that I need to do pi times the integral, and then I need to take my function, square root of sine of x in this case, and I need to square it. Okay? There's the pi r squared, the dx is the height of the thing. Okay?
So basically, in those questions when they ask for finding the volume of the solid form by revolving, we just put the function, square it, and multiply it by pi. That's it.
Well, you got to integrate it.
Well, yeah, but I'm talking about put the function inside the integral. That's what I'm saying.
Yeah, yeah. Okay. Now, one thing I will say, make your life easier by keeping the pi outside the integral. Just get your answer as normal, and then multiply it by pi. Alright, so the integral of sine is a negative cosine. So I have negative cosine x evaluated from 0 to pi. Okay, notice that pi is still out there. So I have a negative, what's cosine of pi?
1.
1.
No, it's negative 1.
Negative 1. There we go. Negative 1.
Silly gooses.
Okay. Then minus
Silly geese.
a negative, what's cosine of 0?
1.
1. So be careful with your negatives. We have pi times 1 plus 1. So 2 pi. Were we given units of measure here? No. So, by the way, what would our units of measure be since we're dealing with volume? It'd be units cubed. Okay? So you can write it units cubed or cubic units. All right? Does this make sense?
Yeah.
It's a pretty simple formula. I mean, you just got to know the formula.
Yeah,
But it's a pretty simple formula to work with. Okay, so here's a case where we have something a little bit different. Okay? And that is, we're not revolving it around the x-axis, we're revolving it around some other horizontal line.
You just do minus 2.
Okay.
Otherwise,
Well, let's see what we're dealing with here, okay?
it goes 1.
If I'm revolving it about a line that's not a coordinate axis, okay, I have f of x in this case is 2 minus x squared, all right? The key to this one is that you have your f of x, and you have the line that you're revolving it around, which is the 1. So to get this radius, you're going to do r of x, you're going to do the function minus 1 in this case. So with that being said, our r of x here is going to be 2 minus x squared minus the 1. So we have a 1 minus x squared. And essentially, if you think about it, what we're doing is we're translating the whole thing down 1 unit. It's a vertical translation to make the line that we're revolving about into kind of the x-axis. Alright, if I shifted this whole thing down 1 unit, then that would put me revolving around the x-axis now. Okay, so we're going to do the volume equal to pi times the integral from -1 to 1 of 1 minus x squared dx. Alright, so we got to FOIL and integrate. Integral from -1 to 1 of 1 minus 2x squared plus x to the 4th dx. So we have x minus 2x cubed over 3 plus x to the 5th over 5. Evaluated from -1 to 1. And don't forget the times pi. So we have pi times, if I plug in a 1, I get a 1 minus 2/3 plus 1/5. If I plug in a -1, which I'm subtracting all this, I get a -1 minus a negative, so plus 2/3 minus 1/5. So this whole thing inside here simplifies to, let's see, a 2 minus 4/3 plus 2/5, which is, let's see, 2/3 plus 2/5 is going to be 10/15 plus 6/15, so 16/15 pi units cubed.